So for this problem, we start out with a power supply, a solenoid, and a ring that are all connected by a current. We're also given that the ring is of a radius R2 and is of a resistance R. The current through the wire is I1, which is given as P minus KT, where P and K are both constants. This means that the I at time 0 is just P, because T times K, if T is 0, would just be 0. So you'd end up with just P. We're also given that the solenoid is of a radius R1, has turns N per length D. The first part is to figure out the magnitude and the direction of the magnetic field at the center of the ring. We've also set up the axis system as plus X in the direction of the solenoid. So the first part is to figure out that there's going to be two magnetic fields. The first one is going to be from the solenoid. So we're going to have the magnetic field net is going to be equal to the magnetic field from the solenoid. And we're also going to have a magnetic field that's going to be induced by a current that's going to run through this ring. And that current is going to be induced by the generated magnetic field, which will then create a flux change. Because we're given that the current is going to be changing, which means that the magnetic field will be changing as well. So along with this magnetic field of the solenoid, we're going to have a magnetic field that's going to be induced, and that's going to be from the ring. Now, we need to figure out the magnetic field from a solenoid, which, if we look on our equation sheet, we can see that the magnetic field from a solenoid is equal to mu naught times little n times I. But we have to figure out which direction this magnetic field is going to be moving in. So we know we have a current that's moving in this direction, and then we'll be passing through a solenoid. But we have to figure out if the current's going to be moving through the solenoid, where the magnetic field will be. We're given that the solenoid is creating a current in this direction with the right-hand rule, which means that the magnetic field will point in the direction of our thumbs, which will be in the positive X direction. So we know that the magnetic field of the solenoid is going to be in the positive Y direction, positive X direction, positive I. We also know that N is equal to and directly related to N and D. So we can substitute in N for N over D. So we end up with mu naught times N over D times I, and it'll still be in the positive X direction. We also know what the current is because we're given the current is equal to P minus KT, so we can substitute in that as well. So we're given mu naught times N over D times the current, which is modeled as P minus KT. This will still be in the positive X direction. We now have to figure out what the current is from the induced current. This is from the solenoid. We're told and shown by this equation that the current is going to be slowly dropping, which means that the magnetic field is going to be decreasing. And if we've already figured out that the magnetic field is moving in this direction, then that means the changing magnetic field will have to be moving in the opposite direction if it's decreasing, which is this way. This means that we need to have a flux change that will be created by this ring that's going to oppose the changing magnetic field, which means if the magnetic field is already changing in the negative X direction, this current is going to try to produce a magnetic field that is in the opposite direction. This means that the only way the ring can create a magnetic field in the positive X direction is by the right-hand rule to have a current that is rotating in this direction as well. So we know that the current from the ring is going to be moving in this direction. Knowing that, we know that the magnetic field is going to also be in the positive X direction. We need to figure out what the magnetic field's magnitude will be, though, which we have a formula for in the equation sheet. We know that the magnetic field from a ring at the center of the ring is equal to mu naught times I over 2r, where r is the radius of the ring, so we can just go ahead and substitute in r for the radius of the ring, which is r2. Knowing that, we also have figured out that this magnetic field will be also in the positive x direction. This means that the total magnetic field will simply be mu naught times nd times p minus kt plus mu naught times I times divided by 2r2. Now, this isn't the current that we're given. It'll be of some induced current that we would have to calculate somewhere else. So this is an I induced current. It's not equal to P minus KT. And that is the final answer for the first part of the problem. It would just be to add these two together. The next part of the problem is to figure out the magnitude and direction of the induced current in the ring. We've already figured out that if the magnetic field from the ring is moving in this direction, then the current has to be moving this way. For the question, it says to state the direction from looking at the right end of the solenoid, which means that we would rotate our fingers this way to look at the right end of the solenoid. This means that we can see that the direction is going to be counterclockwise. For finding the magnitude, we have a couple of equations that we'll have to use. We know that the EMF induced is equal to negative d phi over dt. We also will need to use Ohm's law because we're given and we're going to find resistance and an EMF to find the resulting current. So we're going to have to use Ohm's law, which is I induced is equal to EMF induced over R. We're going to solve for the EMF induced, and we are given that R. So now, if we're going to try to find EMF, we need to try to find d phi over dt. And the first step of finding d phi over dt is to simply find d phi. So to find d phi, we have to just find phi. So we know that the phi created by the magnetic field is given by this from the formula sheet. We have to figure out what B dot dn would be. We're shown that the ring is flat like this, and the induced magnetic field is going to be perpendicular to that, which means that B dot n is going to be times the cosine of 0, which is just 1. So we know that B dot n dA is simply going to be BA. But the area we're concerned with is not the ring, it's the solenoid. So that's going to be important to remember. This is given by mu naught times n over d times p minus kt, and that is our equation for the magnetic field of the solenoid. And then we have to multiply by the area, which is the area of the ring, not the area of the ring, the area of the solenoid, which is pi times r1 squared. Now, if we're going to try to find the EMF induced, we have to take d phi over dt, because we're told that we are only concerned with the magnitude, because we've already figured out the direction. So now, to find d phi over dt, we are already having an equation for phi. So if we want to try to find phi, we have phi, and if we want to find d phi, then we're going to have to take a derivative. So we're going to have to take a derivative of all of this. This isn't so difficult. A lot of this is all constants. Mu naught, n over d, pi, r1 squared are all constants if we're taking the derivative with respect to t. So we know we're going to have mu naught times n over d times pi times r1 squared. And then we're going to not take an integral. We're going to take a derivative of p minus kt with respect to dt. So now, how we're going to take the derivative is quite simple. The p is going to end up canceling out, and we're going to be left with k. Now, it would be a negative k, but we know we're just concerned with the magnitude, so we don't need to care about the positive or the negative part of it. So now, we've got all these constants that we can then multiply by the k, which we've just taken the derivative of. So we know that the EMF is going to be mu naught times n over d times pi times r1 squared times k. So now we figured out the induced EMF, so now we have to try to find the induced I. The induced I is going to just be the EMF over the R. Now, we figured out what the EMF is, and we know that the resistance of the wire is just of resistance R. So since we're not given any numbers, we just have to multiply or divide by R. So the induced I is simply going to be everything in the EMF divided by R, which will be mu naught times n times pi times r1 squared times k over the d from earlier times the resistance. So this will be the magnitude of the I. And just to reiterate, we know the direction will be counterclockwise because it's producing a B field, which will then create a current in this direction, which, looking from the right side of the solenoid, will be counterclockwise.